All right, folks, your favorite physics teacher here, and it's time to go over the Physics C mechanics free response question. But first, I'd like to talk to you about my website, findphysics.com. This is the world's finest physics, and this is where you can go to find out about professional development for physics teachers, for math teachers, and also we provide one-on-one or small group tutoring online for physics and math students. So, probably physics teachers are going to see this. So I wanted to let you know about my workshop that's 4 days in Frisco. It's in person because we're going to do lots of hands-on activities. We're going to talk about remediation techniques, better ways to teach like Newton's third law and other confusing concepts, rotation. We're going to see some fluids before it gets added to AP physics. But it's for anybody who teaches mechanics, not just AP teachers. Let's see. So go to findphysics.com. That's PHINE fit-physics.com. If you're interested in more information, see a session agenda, or to access the registration form. You can steer your students there if they want to reach out for one-on-one tutoring from somebody who has a lot of experience with AP Physics. And feel free to direct your math teachers to my professional development workshop this summer for math teachers, where we're going to do lots of hands-on stuff that's going to be kind of physicsy stuff. If you saw it, you'd be like, hey, that's like Bernoulli, that's Hooke's Law and that kind of stuff. But it's going to be specifically for grades 6 through 12 math, hands-on to engage them better. Because if your math teachers do better, then you're going to do better. All right. So there we go. So special thanks also to the College Board for providing us with these wonderful AP exams, and also to Golden Corral, just because I like to eat there. All right. So here we go. Now, the mechanics came in 2 sets. We have set 1 and set 2. I'm going to warn you, I've not actually seen these questions yet. I only saw them enough to write set 1 and set 2 on them. I'm going to alternate between set 1 and set 2. I have no idea which ones your students took. I think that my students, some took one and some took the other. I don't understand how that works, but whatever. Let's just run with it here. Okay, a block sitting horizontal surface, push against spring P is attached to the wall, compressed spring distance X, as shown in figure 1. The block is then released from rest. The block slides along horizontal surface up a ramp. H max P is maximum height, no friction. And okay, obviously we're environmentalists here. Look at all that well-used space right there. Okay, a student compares H max P for spring P with the maximum height H max Q achieved with a different spring Q. Each spring exerts a force magnitude F on the block that varies the function of the distance X that the spring is compressed, as shown in figure 2. For spring P, we have just good old F equals KX. That's just good old Hooke's Law. And for spring Q, we've got this monstrosity with the 1/2 power. And here we go with the 1/2 power and with the straight line. All right. For the experiment, we've got 2 pages into this. And all we're doing is, I'm assuming, free body diagrams. Let's see. On the following dots, representing the block in trials 1 and 2, draw and label the forces, not components, that are exerted on the block at the instant the block is released. Okay, we're going to go to block is pushed against one of the springs, compressing the spring at distance 0.1 meters. So 0.01 meters. So I'm going to mark that right there. That seems important. All right. Each force must be represented distinct arrows starting on point away from the dot. The lengths of horizontal vectors should represent the relative magnitude of the horizontal force and lengths of the vertical vectors to represent the vertical force. Okay. Okay, so when are we doing this? The instant the block is released. So we're going to know for sure that the block has an mg 1, 2, 3, 4, 1, 2, 3, 4, and a force normal. There's going to be an mg 2, 3, 4, and a force normal. Okay, let's go back to one of the previous pages. Looks like the direction of the force will be to the left. So spring P exerts less force. So I'm going to only give it 2 boxes. The force of spring P, but I'm going to give this one a longer one because it looks like spring Q exerts more force. The force of spring Q. All right, everyone, it took us 2 entire pages. We love trees here at the College Board. Okay, what features of the graph in figure 2 could be used to estimate the work done by the block on each spring as the spring is compressed? Okay, I feel like they just want me to say that, work is the area under a force versus distance graph. Work is the area under a force versus distance graph, right? So maybe what I'm going to say is if the block is compressed 0.01 meters, then take the area under that spring's graph x equals 0 to x equals 0.01 meters to get the work done on that spring. Now, why am I going through all this detail? Because every time I've ever seen this on AP exam where the students have to say, oh, I have to take the area, they have to say from where to where on the graph. So I'm trying to word my response so that I can say where, from where to where. So if they just take the area, your students say just take the area, it's unlikely they'll get all the points. They really need to say the area from and to, because areas have a from and to. They call that what, limits or bounds on the integral in calculus, but I call it a from and to, from and to, in case you can't get the gag. Okay, there's one compression distance for which the maximum height reached by the block is the same regardless of which spring. There is one compression distance, x naught, for which the energy stored in the spring is the same regardless of which spring. That's what they're really getting at. Predict whether the value of x naught is greater than, less than, or equal to 0.04. So why they choose 0.04? Because that's where that crossover. But it's not 0.04 because then you have more energy stored in spring Q, more area. So I'm going to say it is greater. It's going to be greater than 0.04 at, let's go for blue now, at some x naught where x naught is greater than 0.04 meters, the energy stored in each spring is the same, since this results in both graphs having the same area for, zero is less than x is less than x naught or whatever. If I'm going to say this, I'm going to say at x equals 0.04. Okay, what did we say? Spring Q, meters, spring Q has more energy because more area on the force versus displacement, whatever, right? That's probably a lot more than I needed, but sometimes you add a little bit extra understanding. The readers will be like, this kid knows what they're talking about, right? They're going to give your kid the benefit of the doubt. All right, on the axes provided for both spring P and Q, sketch a graph of the maximum height reached by the block as a function of the distance each spring is compressed. I feel like this is a trap, okay? Admiral Akbar is not here to tell me whether it's a trap, but let's have a look here. I think I need to say that if this is spring P, this is P. If F equals Kx, then potential energy equals 1/2 Kx squared. That's just a basic integral. Just good old-fashioned integral. I'm going to say 1/2 Kx squared becomes mg H max, right? So then I see a quadratic relationship. Okay, now that is 0 to 0.1. So I'm going to use pen here, and I may regret it. Here we go. All right. Clearly labeled the curve for spring P and for spring O. So this is a P right here, okay? Now, remember that all AP readers are colorblind, it turns out. That's a qualification that they actually test for. So your student can't say the pink one is P or whatever, right? Because they're colorblind. They can't see any kind of color, okay? So there you go. Q. What was Q? Q was F equals CX to 1/2. So F equals CX to 1/2. So basic integral raised up to the 3/2. So 2/3 C to the 3/2 power. So I'm going to say 2/3 CX to 3/2 power equals mg maximum height. And I think that's also a curve It kind of looks like a parabola, but it's not exactly. But there's going to be more energy stored in Q. So that means you're going to go higher. It's going to be more energy stored at this 0.01, right? So I'm going to be all like kind of like that for Q, and I'm going to hope that that's correct. Okay, I don't know if it is, and I don't know if I even care. Oh my gosh, how many parts does this have? Okay, spring Q is attached to the wall. Is at equilibrium. Block A, that. Block B, that. Oh, okay. Block A is held at rest at the top of the ramp and the horizontal surface. The student releases block A and it moves down the ramp and collides with block B. The change in the vertical height of block A is that much. After the collision, the blocks stick together and move to the right, compressing the spring, no friction. Calculate the velocity of two block systems immediately after the collision. I have to do two things. I'm going to have to first do an energy. So step one is an energy, where I'm going to say a mass of A, G, the capital H is going to become 1/2 mass of A, the V before the collision squared. Okay, so the V before the collision squared is going to be the square root of 2G, the H. And then now I'm like, I should have come prepared to the AP exam with my calculator ready, okay? Okay, now I hope you told your students to set their calculator to degrees in case it comes up, because AP calculus, they should set it to radian, shouldn't it? All right, this is going to be an ugly number no matter what, because 0.75 does not comport with any nice, G equals 10 type numbers. So what I've got is I've got like 3.83. All right, that's about 3.83 meters per second, right? Now we're going to do a good old momentum. We're going to do your friend and mine momentum. Okay, so momentum is going to be the mass of A. The V before the collision is the mass of A plus the mass of B after the collision. Okay, good old, all this. Okay, so 0.12, 3.83. Okay, 0.12, 0.07. Be final. Okay, so I'm going to take 0.12 times this phone number, and I'm going to divide it by 12 cents plus 7 cents. If I can do this correctly, okay, just double checking my numbers. Let's see if we do this right. So the final velocity is 2.42 meters per second. Calculate the maximum compression of the spring. Okay, so I know I'm going to use energy here, because when the spring is the most compressed, then all the energy is potential. I mean, it might even write when the spring is most compressed, all the energy is potential energy. And I already showed that if x equals cx to the 1/2, that becomes u equals 2/3 c to the x to the 3f power. Okay, what was the c? Oh, I've got like some more papers here than when I do my freaking taxes. Okay, so u is 2/3 times 20. That's not even a pretty number. X to the 3/2 power. And now I'm going to have to take that, geez, what is that, 40/3 x to the 3/2 power. I can't even bring myself to do this. That came from the 1/2, the m total, and the v final squared. Okay, so I'm going to take 1/2, the m total, whatever that is, 2.42 squared meters per second. So 1/2, 0.19, this squared. Okay, so that's the left, that's the right-hand side. So let's multiply by 3 over 40. Okay, now I have to raise this, I think, to the 2/3 power, and I think I'm going to get a distance of 0.12 meters. All right, 40 over 3, x to the 3/2. I feel like I really want both sides of the equation always be there. I have no idea if I did this right. This is the first time we've even looked at these, okay? Oh my gosh, this problem has more steps than AA. Okay, spring. How many parts is this actually? Like, seriously, okay? 1, 2, 3, 4, 5, 6, 7. Okay, there's not an E. Okay, 7. Okay, not as many steps as Alcoholics Anonymous after all. Spring Q, thanks for the reminder, is replaced by a different nonlinear spring, glorious, spring R. Okay, and the procedure described in part C is repeated. What was the procedure? Okay, we're gonna maybe it's gonna hit into some garbage like that. Okay, for this spring, it's dx to the 1/2. The maximum compression of spring R is great. If it's greater, then that means that the spring is more loose, like your mother. And if it's more loose, then the D has got to be less. And by the way, College Board, this is the way you do it, by the way. Can I just tell you, right, how many times have you done this thing where it's like, indicate whether A is greater than, less than, or equal to B? Greater than, less than, or equal. No. Will you do it this way from now on, please? This is so much more clear. C is less than D, C is greater than D, C is equal to D. The whole greater, less, or equal to, that requires me to decode the English language, and it can get awfully confusing, can I just tell you? This is glorious, okay? So C is, no, but that's not even the right answer. It's C was greater than D, right? Briefly justify your answer. So I'm going to say the same energy should be stored by the spring, whether, okay, at maximum compression, okay, at maximum compression, whether spring Q or spring R, right? Now, what am I going to say about that? I'm going to say the U was 2/3, C or D, right? X to the 3/2. So if U is the same, but X is more for spring R, then D is less or something like that, right? Okay, that's my answer there. All right, that took a lot longer than I thought. Oh my gosh, I'm only 1/6 of the way through this. Okay, so here we've got here. Okay, so when I saw this question, as I was running it off, I saw the word foam and I saw the words scientists have created a new type of lightweight foam. I was like, wow, what an incredibly stupid question this looks like. And then, of course, I was like, wait a minute, this looks awfully familiar, doesn't it? Have I seen this question before? Yeah, I have. Okay, so if you didn't figure out what I just showed you, then you probably shouldn't be teaching AP Physics. All right. So, scientists, it's been what? When did I send this off? Sometime in 2021. So it's been at least 18 months since I've seen this. Let's put it that way. Performing experiments to investigate the properties of the foam. Cart A is 1,000 kilograms and cart B is 2,000. Did I use those numbers? Oh, wow, I really did. Okay, so we basically got a small Kia and a Ford Escort, if they even still make those. A piece of foam with negligible mass in front of cart A. Cart A moves constant speed toward cart B. Time equals 0. The foam makes contact with cart B. The foam remains contact for 0.5 seconds after which the carts separate, and both carts move constant velocities. Okay. The graph shows the velocity VA of cart A. I didn't do this, did I? Nope, that's not anything I've ever seen before. Probably should not be showing you that, actually. Okay, so the graph shows the velocity of cart A as a function of time t for the time interval when the foam and cart B are in contact. What features of the graph could be used to estimate the displacement of cart A during the collision? Okay, so now you notice what we're doing is we're trying to ask the same questions between the two sets or test the same learning objectives. So here we're going to say you're going to take the area, and you're going to take the area of the velocity versus time. Please say the graph you're talking about and say from and to. From time equals 0 to time equals 0.5 seconds. Okay, determine the speed of cart B at t equals 0.5 seconds. Okay, so what am I going to say? This is conservation momentum. So I'm going to say mass A, VA initial equals mass B, VB initial plus mass A final, I mean to say mass A, VA final, or whatever. I can't write anything in alphabetical order. Okay, that's my problem. That's your problem. That's my problem. I don't even care whose problem it is. Shut up. Okay, so we've got 1,000 times 5. This is 2,000 times V. Okay, and then this is 1,000, and VA final is 1. This is awfully clever. Okay, I did not write this part. This is a really clever way of asking about conservation momentum, something that's like really at the regular physics level. They have to read off the graph. So kudos to whoever you are who got this, who made this up, and for making it pretty numbers also. That warms Mr. Friendly's heart. Okay, so 2 meters per second, yay. On the following grid, draw a smooth curve of the velocity cart B as a function of time. So it's going to go from 0. It's going to end at 2. And it's going to look like this shape, only the opposite. So kind of like that, okay? Okay, for that, the velocity of cart A can be described by that function. Okay, better you than me. Calculate the magnitude of the maximum net force acting on cart A during this interval. Wow. So basically a calculus question. Maximum net force occurs where at the same time that acceleration is a maximum. M, the maximum acceleration, right? So what is acceleration? It's going to, I can't do 64 times 3. Who do you think I am? 64 times 3. Okay, 192. 192 t squared minus, I can't do 48 times 2. Who do you think I am? Okay, 96 t, the 5's gone. That's the acceleration. Now, how do you find the maximum of anything? To find the time of maximum acceleration, okay, set the derivative of acceleration equal to 0 and solve for t. So this is a classic solving for a maximum, right? Which is really an A-B, very A. It's really not even A. It's O, calculus is what it is. Like loser calculus can do this. 192. Now, what can I not do? Multiply 192 by 2. I can't do that. 384t minus 96, that's going to equal 0. So what is 96 over 384? Is it a quarter? Oh my gosh, it'd be so great if it was 0.25. Oh, yes. All right. The time of maximum acceleration. That's 0.25. Whoever you are who came up with this, I did not write this part, right? Whoever you are, thank you so much for these pretty numbers. That makes me so happy. I freaking hate ugly numbers. Okay, so time of maximum acceleration. Now we're going to find what the freaking maximum acceleration is. We're going to do 92 times 0.25 squared minus 96 times 0.25. Okay, I hope you use my calculator correct. Okay, so negative 12. That makes perfect sense because we have a negative slope there. Okay, the magnitude of the maximum net force. So the maximum magnitude of acceleration, and I want to actually kind of show this, right? Like I'm trying to model good behavior on the AP Physics exam. If you're a student watching this, you're never going to see it again. But hopefully you'll never see that AP Physics exam again. But if you're a teacher, you know, like this is what we're trying to do. We have all this space. Not that you have to fill up the space. We kind of want to show what we're doing. We don't want to skip too many steps, confuse the reader. Okay, now F maximum net force is MA maximum, which is going to be 1,000 times 12, which is 12,000 newtons. All right, draw a smooth curve of the magnitude of the force acting on card A as a function of time. Clearly indicate the value of the maximum net force. Okay, I'm just going to tell you right now. I know that the maximum net force is going to maybe be about right there. Actually, I take it back. Did I really mean to do that? I mean, I guess I meant to do that. I probably would have been a little bit more careful if it were me. Okay. Well, let's see. This was, what was this? 12,000 newtons, right? Okay. And I know that this is actually going to be a parabola. This is going to be a parabola. Okay, so this is a parabola. So I'm going to try and draw the best parabola I possibly can. All right, so maybe that's a, you know, how do you know it's a parabola, Frensley? I know it's a parabola because the acceleration is also a parabola. So there you go. I mean, you can graph this if you want. Actually, if you graph this, you're actually going to get this, A versus T, but that's because it's negative. So the force has the same graph, but since it said magnitude, we're going to take the absolute value of it and make it positive. The foam is removed from the front of cart A, and the experiment's repeated. The carts collide, A and B having the same initial final velocities as in the original collision. The time intervals during which the carts are in contact are different in the collision with the foam and the collision without the foam. In the collision without the foam, cart A is in contact with cart B is shorter duration than the original collision when the foam was present. All right. And the same initial. Okay, so the velocities are the same, but the time of the collision is less. Okay. For the original collision, when the foam is present, the magnitude of the average net force is F1. Then it's F2. All right. So F2 is going to be greater than F1. And how do we know that? Because delta momentum equals F delta T. Since the V initials and V finals are the same with and without the foam, the delta P is the same, right? Without the foam, the delta T of the collision is less. So more force without the foam. And that should be pretty easy for anybody to figure out. All right. That was just question 1 of each set. Now we're on to question 2. Are you still even watching this? If you are, then I commend you. All right. A student makes a torsional pendulum by suspending the uniform disk of SM, radius R, light wire torsion constant K that is attached to the center of the disk as shown in figure 1. The rotational inertia of the disk is given by that. The student conducts a relationship between the period of oscillation and the number of identical disks that are suspended from the wire. Okay, so that makes sense, right? The student starts with a single disc, holding the disc at a small initial angular displacement from the untwisted position. The student releases the disc from rest. The pendulum oscillates. It's going to go whoop, 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 whoop. Okay. The student records the period of oscillation to a single disc. An additional disc is attached, shown in figure 2. Repeated for 2 and then up through 10. Okay. Using this, derive an expression T as a function of N. Well, here's the deal. I'm just going to say I is N times 1/2 mr squared, which is 1/2 mr squared for each disk, right? Okay. A 1/2 mr squared for each disk. A chicken in every pot, a car in every garage, a cancer in every brain, and a 1/2 mr squared for every disk, right? Okay, so there we go. So I'm just going to replace that. T equals 2 pi square root of, I guess I'll put the 1/2 out in front, 1/2 n mr squared over the K constant or whatever. Do we ever see the K constant? It just says torsion constant right there, but it doesn't actually say anything more about it. All right, that's it. I'm just going to put a circle around it. Does that really derive? Sure, whatever. Okay, the potential energy stored in the torsional pendulum is that nightmare. On the following axis, sketch a graph of the maximum kinetic energy as a function of N. Okay, wait a minute. Okay, my spidey sense is tingling right now. Are we always going to use the same? If we're using the same theta, then the K max would be the same the whole time. Now, why would the K max be the same? The U is the same if the same chord is used, which it is, and the disks are released from the same theta naught, since the U becomes the K maximum, or the U initial, I should say. There's no dependence on the number. Now, they'll move slower and have a longer period, but they will have the same kinetic energy. Okay, the entire page was just for that flat line. Oh my gosh, okay, screw you, Forests. The student plots T as a function of 1 over N. I'm going to get out my super pink super ruler here. Okay, draw a best fit line for the data. Draw a best fit line for the data. Draw the best fit line for the data. Draw the best fit line for the data. And it has a couple of points above and a couple of points below. The student previously determined that the radius of the disk was that. Okay, my disk has a much bigger radius. It found that the K is that. Using the graph, calculate the mass M of a single disk. Okay, so period equals, what was that? 2 pi radical 1/2 n mr squared over the little kappa K constant. So I'm going to say, oh, I don't want to do this. I really wanted it to be T squared versus N. Why do you make me deal with a radical? Okay, so if I do T over radical N, I'm just going to pull him out and bring him down, but he's still under the radical. I get 2 pi square root of mr squared over 2K. And so this then would be the rise because it's on top. This is the run. So this entire thing is the slope. So let's actually get the slope, shall we? Show me. Me, I'm the only one doing this. You're just watching me do this. Okay, that looks like a good point to use for my slope. Where's another point I'm going to use for my slope? Oh, I think I'm going to use that point right there. Okay, that's 0.7 rise and what the shit? 2.6 run. Okay, so rise of 0.7, run of 2.6. Yes, actually do put the rings around the points. You're taking -0, -0. Okay, it's whatever this is. Whatever 7 over 26 is. Okay, what are the units of that? That's actually seconds. That's actually a number of seconds because N has no units. It turns out it's a countable number. Okay. Oh, I got to set that equal to this. I'm running out of brain, and I don't have any. I've got 3 more of these questions to do. Okay, so we're going to set whatever 7 over 26 is equal to 2 pi radical m. Where's the m? What's the m? Did they tell us the m? Did they tell us the m? Did they tell us the m? Oh, I'm supposed to be finding that out. Duh. Okay, let's see. The r is 0.2 squared all over 2, and the k constant is 1.6. So now I'm going to take this, and I'm going to divide by 2 pi. Take 7 over 26, and I'm going to divide by, in parentheses, 2 pi. Don't divide by 2 and pi separately, or else the calculator will divide by 2 and then multiply by pi. Let's square that SOB, and then let's multiply by 2 and 1.6, and then we're going to divide by 0.2 squared, and this is what I say. I say that the mass is going to be like 0.147 kilograms. You know what? There's scales. They're pretty cheap at Harbor Freight Tools. Just put the disc on a scale, man. Okay, the student finds a value given by the manufacturer for the mass of the disc. There's no good place this can go. I haven't read the rest of it, and I'm already pissed. Is less than the value determined experimental in part. I'm so bad at this. In C2, determine a single source of experimental error that could result in the observed difference. Okay, so the m, the true m, is smaller than we thought. So it's possible that the student either had the true k constants. I'm going to list some possibilities. The true value of the k constant is less than the student thought. Okay, or it's possible that the student's periods were longer than they should have been, right? You know, maybe they're not very good at using the stopwatch or something like that. I'm not entirely sure what they want to hear there. Oh, is this problem still happening? Oh my gosh. What? Okay, so A, B, which took up a whole page. Okay, well, it just seems like forever. I don't know why. The student repeats the experiment. Why? Get a life, kid. But now the discs have a density that varies as a function. Oh my gosh. Why? Radius, according to this. All right. Would the slope of the best fit line for this new data be greater than, less than, or the same as the slope of the best fit line in part C? All right, I'm not going to lie to you, folks. I don't really know that I can answer that without taking an integral. Like, okay, so the I, okay, here's what I'm going to say. I'm going to say if the I is greater, okay, if the I is, where is this? Okay, if the I is greater, the slope, the period in the slope will be greater. Then the period is greater and the slope is greater. So I need to find out if the I is greater or not. So I is the integral of r squared d mass. And so what I'm going to do is I'm going to say integral r squared times d mass over d volume. Is there some way I'm supposed to be able to do this without, like, they didn't say that this was the same mass. If they said it was the same mass, but the density is increasing as you get from the center, I still don't know what I would do. Okay, now the volume for a cylinder is pi r squared, the height or thickness of it. So the dV is going to be 2 pi r h dr. So now I'm going to say I is the integral of r squared. This has got to be the wrong thing to do. I'm just going to tell you that right now. Times 2 pi r h dr. And you know what I'm going to do? I'm going to call this from 0 to capital R. Like, I'm just going to do this symbolically. I don't know why I'm doing this. I feel like this is such a stupid idea, and I really should just stop. Okay, so I've got the 0.3. I've got the 2 pi. I've got the h. The 0.3, the 0.3, the 2 pi, and the h. Okay, and I'm going to integral 0 to r of r cubed dr. So then that's going to be I equals 0.3 times 2 pi times h times 1/4 big R to the 4th power. That's the I. Now, what's the mass of one of these? The mass of one of these is going to be oh gosh, are you kidding me? Okay, I don't know the actual height of one of these. Yeah, you might have got me beat, folks. This would be the integral of density d volume 2 pi r hdr. And so this would be, let's see, 0.3 times 2 pi. That's an r squared. So it'd be 1/3 r cubed, right? Okay, so this doesn't make a lick of sense. How did I screw this up so badly? This is r squared. Oh, that's r to the 4th. Shit. Okay, there we go. All right, so I think I fixed that. So now I'm going to do the following thing. I'm going to take I over m, and the I is 0.3 times 2 pi times h times 1/5 r to the 5th, and the m is 0.3 times 2. This has got to be the wrong thing to do. I swear to high heaven, this is not the right thing to do. But I'm doing this the first time right now, and maybe somebody out there might help me. Fuck off. Fuck off. Fuck off. Fuck off. Okay, so I over m is 3/5 r squared. So I is 3/5 mr squared. So I'm going to say that the period is greater than. And why am I going to say it's greater than? I'm going to say it's greater than because the down here, the coefficient, ICIENT, of 3/5 is more than the 1/2 before. You got me. What was I supposed to say? Okay, when n equals 1, the maximum angular speed is found to be blue. When n equals 1, the maximum angular speed of the tornado with the non-uniform disk is blue. Which of the following correctly compares that? Okay, the maximum. Okay, right. Since the non-uniform disk has more rotational inertia, but the energy total is the same, then by maximum speed equals 1/2 I maximum omega squared. By that equation, more I for the non-uniform disk means less maximum omega. All right. Okay, what fresh hell is this? Okay, we got the K's, we got a couple of springs. Relationship between period of spring and spring and attached springs. The student starts the block mass M, attached single ideal spring concentration in figure 1. The student holds the block so that the spring is neither stretched nor compressed at vertical height 1 of sensor. So release the block from rest, records the period of oscillation for the system consists of single spring the block. Okay, 2, 3, 10, however many you need to do. Okay, derive an expression for T as a function of N. Okay, so the K effective of N parallel springs is NK. So the period would be 2 pi square root of NK over M. Okay. Sketch a graph of period as a function of N. Is it seriously the same? Oh, no, that's not what it is. Sorry. Okay, I didn't mean that. That was not like the sorry, it was not like the kinetic energy before. That's not what it is. Instead, it's going to look something like this. Like, grade this one, please. And why? Because 2 pi radical NK over M. That means period and square root of N are directly proportional, or period and N have what I call a root relationship. Okay. All right, one entire page for that. All right, where's the pink ruler? All right, the fearless pink ruler. I'm not even reading the rest of this. Are you forcing it to go through the origin? Yeah, I am. You got a problem with that? You can go stuff it. Draw the best fit line. the mass of block, get the value of the K. Okay, so I'm going to say the slope of this looks like, is that 13? That would be 13. 13 minus 0 over 1.1 minus 0. So it's whatever 130 over 11 is. I don't honestly care. All right, T. Oh, T squared versus, that's so nice of them. NK over M, T squared will be 4 pi squared NK over M, which means, why do I have a problem with this? Oh, because I put K on the top and not M. Well, why didn't you tell me? All right, why didn't you tell me? Why didn't you reach across time and space? It's M over N times K. All right, this is a good time to figure out that that's a problem. All right, I meant to say it's M over N times K. I'm not using a formula chart here, folks. Yeah, it's T equals radical M over K, not K over M. Okay, I bet you're sitting there wondering, is he ever going to figure out that he did that wrong? Yes, I finally did. Okay, so then wrong. Okay, M over N times K. I told you I hadn't rehearsed this. Okay, I'm not Mr. Perfect at physics either, but I eventually figure it the frick out. Put any other mistakes in the comments, but watch the end of the video in case I correct myself. If I bring this sucker up here, you get NT squared equals 4 pi squared M over K. That's really the same as over N to the negative 1. So this is going to be the rise. This is going to be the run. That's going to be the slope. So let's set 4 pi squared times 1.5 over K equal to whatever 130 over 11 is. Okay, so I'm going to take 4 pi, get rid of this crap, 4 pi squared times 1.5, and then I'm going to divide that by whatever 130 over 11 is, and then I get a spring, oh my gosh, you're kidding me, 5.01 newtons per meter. Wow, that spring, it really is looser than your mother. Geesh. Okay, so the student finds the value given by the manufacturer spring is larger than what we determined. Determine a single source of experimental error. Okay, so as I look back at this, if the K should be higher, then that means either the mass should be higher or the period should be lower. So you maybe say the T, the student measured, was higher than it should have been. I don't know how much detail, like why would that happen maybe? Or the M is actually more than like 1.5 kilograms or something like that. I don't know. Heck, you could even say this, that the slope is, I should have drawn a less steep slope. Maybe you could have said that. I don't know. Oh my gosh, it hasn't ever stopped yet. The student conducts an investigation in relation to period and identical springs arranged the blocks horizontally. No friction, thank goodness. The block has displaced the same horizontal distance and release from rest. The student plots that. Would the slope of the best fit line from this new investigation be the same? Okay, it's the same. Why? Because the period does not depend on whether the block oscillates horizontally or vertically, right? Okay. When n increases, will Vmax increase, decrease, remain the same? Okay, it's the same horizontal. Then it's going to increase, and here's why. You're going to have potential energy becoming kinetic energy. 1/2 the effective spring constant x squared becomes 1/2 mv squared maximum, right? So as more springs are added, right, the K effective increases. If X is the same and M stays the same, the Vmax must increase. Oh my gosh, I'm not even done with this yet. Oh, I've got 2 more number 3s to go. All right, the system has a small sphere, horizontal surface. We got this rod, mass 2m, length L, attached one to the pivot. The R, What's the R? Oh, the radius of this thing is way the frick less than the length of the rod. There's no friction between the surface and the sphere. Okay. Oh, it's going to be one of these. It's going to be one of these where it's purely translating, and then it's going to start rotating. Okay, because of the friction. Okay. The rod is held horizontally. The total rotational inertia of the rod, the rotational inertia of the sphere. Okay. After the rod is released, the rod swings down and slaps the sphere. As the result of the collision, the rod is stopped. Oh. And the ball initially slides without rotating to the left across the horizontal surface. The angular speed of the rod just before striking the sphere, that's going to be energy. Okay, so we're going to be talking energy here. So if this length is L, cursive L, then the center of mass will change by 1/2 an L height. So we're going to have capital M for the rod. G times this delta height becomes 1/2 I omega squared. This will be mg 1/2 L, that's the height change, equals 1/2, what's the I? 1/3 ml squared times omega. I'm going to call that omega initial, like as in right before the collision. Okay, so meh, and one of the mehs. Okay, so the G, 3G over L equals omega versus square root omega. That's the omega initial right there. Okay. Derive an expression for the linear speed of the sphere immediately after colliding. Now we're going to do angular momentum. The angular momentum of the rod before is going to exactly equal the angular momentum of the sphere after. So this is going to be I omega initial, and this is going to be MVR. There's the sine of 90 is 1, so there's really no need for a sine theta here. Let's see. This is 1/3 mass length squared. This is the square root of 3g over L. That's not happy for me. And then that's going to become, okay, I'm taking the angular momentum about the pivot right here. So if I do that, this will be M, V after the collision, R, which is L. That's the distance from the pivot. Okay, so what we're going to do is we're going to eliminate one of these L's. And this M is actually 2 little m's, so then I can contract those down. Okay, so basically, yeah, I just got my big final right now. 2/3 L times the square root of 3g over L. Now, if you wanted to, that's really the same thing as 2/3 the square root of 3gl. Or you could say, what could you say? 3/4 gl. I don't know. I hope I did that correctly. Okay. After sliding a short distance at time 0, the sphere encounters a region of horizontal mu. Bring at point A. The sphere begins rotating while sliding and rotates without sliding, also as indicated. B. Draw and label the forces that act on the sphere. Okay, so you're going to have a force normal. You're going to have an mg. I believe the friction force will be this way in order to get your counterclockwise rotation up. Okay, the linear velocity is a function of time t. I'm going to say velocity equals at plus v naught, and I'm going to make the left be positive. Okay, the left is positive, right? Now, the v naught is radical 4/3 gl. Now, what about the a? Well, so the net force equals ma, but the only net force is friction equals ma. So that's mu force normal equals ma. You are sliding, so this is kinetic friction. It is not less than mu force normal. It is exactly mu force normal. Umg equals ma, m's cancel. So this is going to be mu g t plus v naught plus whatever. Okay, I think that's it. Is that all there is to it? It's just the linear velocity as a function of time t. Okay, the angular velocity, so we're going to do omega equals alpha t. Oop, that's a negative up there. Sorry. You are not speeding up because of that friction. You're actually slowing down. Here's the direction of velocity, which is not a force, so I'm just going to put it out there. V equals omega equals alpha t plus omega naught. The omega naught is 0, so I'm just going to mark it out. How am I going to get the alpha? Well, net torque equals I alpha, and the net torque is radius times friction force, radius times mu mg. Okay, this is going to be 1/3 times, let me be careful. Yeah. 1/3, no, sorry, 2/5. What the frick was it? 2/5 little mr squared times alpha, which I cannot plug in a over r because I'm slipping. You can only plug in alpha equals a over r if you're not slipping. So 2/5 mr squared alpha, The M's cancel. One of the R's is going to cancel. Now your alpha is going to be 5 mu g over 2r maybe. So we're going to say omega, and this is speeding up in its rotation. So this is positive 5 mu g over 2r times t. Okay, how much you want to bet? It's going to ask me the time or distance to get it to stop slipping. Derive an expression for the time it takes the sphere to travel from point A to point B, where it quits slipping. You need to know that when the slipping quits, V equals omega r. But V equals omega r is only true when you are not slipping. And friction equals mu normal only works when you are slipping. If you're not slipping, friction is something less. Okay, then when the slipping quits, V equals omega r. Okay, I just forgot what I was thinking just now. Oh, yeah, I'm going to plug in the V. So minus mu gt plus square root of 4 thirds GL. That's the V. The omega is 5 mu g over 2RT. That's the omega. I'm just copying from up here. Times R. R's cancel. Okay, let's bring this over. When we bring this over, we're going to get 4 thirds GL equals 7 halves mu GT. Man, do I not want to do this. Okay, so the time is going to be 2/7 radical 4 thirds GL 1 over mu G. You think I'm going to simplify that? You are crazier than, you're nuttier than squirrel poop if you think that I'm going to simplify that. Derive an expression for the linear velocity of the sphere upon reaching point B in terms of V naught. Okay. Oh, maybe I will have to simplify this. I may be eating my words. V equals minus mu GT plus the square root of 4 thirds GL, right? Okay. So now we're going to do negative mu G times this time 2/7 times 4 thirds GL times 1 over mu G plus 4 thirds GL, cancel, cancel. And now I actually have like terms. 1 minus 2/7 of something is 5/7 of that thing. That's the final velocity. That's my story, and I'm sticking to it. Okay, last one. I think I hear my AP Physics 1 students are coming in. They might be about to be finished. A wind turbine includes a 3-blade system that bitch slaps birds out of the sky onto the ground. No, I'm joking. That rotates about an axis through each end of the blade, as shown in figure 1. Each blade has length L, mass M, and center mass located at L over 3 from the axis rotation. Derive an expression for the rotational inertia of the 3-blade system. Okay. Express your answer in terms of M, L, and physical constants. Rotational inertia of each blade about an axis through its center mass. Okay, so this is going to be the parallel axis theorem. The I of the blade through the end is equal to the I about the center mass plus what I call MD squared, where D is this distance right there. Well, that distance right there, I'm assuming is 2/3 L. Like I'm assuming that that's 2/3 L. So this is going to be 1/18 ml squared plus m times 2/3 L squared. 1/18 ml squared plus 4/9 ml squared. I'm not going to combine those. Oh, I think I am. Oh, no, I'm not. Oh, I don't know what I'm doing. 4/9 plus 1/18 math fraction. Oh, what? You are freaking kidding me. Okay, so 1/2 ml squared. That's the I of one blade about its end. So the I of all the blades would be 3 times as much. 3/2 ml squared. Okay. While the wind blows, the cradle will rock. The 3-blade system operates as a constant angular speed omega. The length of one blade is that. The numerical value of the rotational inertia of the system is that ginormous number. Calculate the time it takes the outer edge of a single blade to complete one revolution. Are you seriously just... what? You mean just omega equals 2 pi over the period? Like, why the shit do I need to know that? Or this? Why do I care? It's omega. Really? All right, so period is 2 pi over omega. That's 2 pi over 2.6. 2 pi over 2.6. That's 2.41 seconds. 2.417 seconds. Is that all you want? What was the rest of that shit there for? Okay. When the wind stops blowing, well, this problem needs to stop blowing. The angular speed of the system decreases. Yeah, it sure. Oh gosh. The angular speed of the system while slowing down is given by the function that modern art, where beta naught's a constant with some kind of units. The appropriate units are 1/seconds. All right. Okay. Calculate the amount of energy dissipated from time equals 0 to when the wind stops blowing until the system comes right. Okay, I'm going to show you 2 ways to do this. One way to do it sucks hose water. I really hope your students didn't do this. I hope they didn't say, well, power is going to be torque times omega, and torque equals I alpha, and alpha is the derivative of omega with respect to time, right? But they could have done this. And if they did this, they would have said that alpha is negative beta naught omega naught e to the minus beta naught t, right? They could have done that and then multiply that by I. So then the power would have been this. It would have been torque I times negative beta omega naught e to the minus beta naught t. That is just the torque times omega naught e to the minus beta naught t. And then they could have actually integrated the power dt from 0 to infinity. They could have done that. Or do you want to know what else they could have done? They could have just said the energy dissipated from t equals 0 to t equals infinity is the same as the initial kinetic energy of the system. 1/2 I omega initial squared. Okay, so there it is. It's 2.6, and then the I of the system, 6.7 to the... Okay, so it's the I of the system. It's 6.7 times 10 to the 6th. I wish this problem would end before my Physics 1 students come in. Oh my gosh, 1/2, 6.7, E6, 2.6 squared, and you get 226246000. All right, that might be somebody's phone number. Joules! All right, that's a lot of joules. Now, I swear, if you do this long, terrible process or this easy thing, you'll get the same number. This is called a misdirection, by the way. That's why I call it with my students a misdirection. It's when they ask you for the energy at the end and you give them the energy at the beginning because it's the same number. How much energy is dissipated? I don't know. I'm just going to tell you the energy at the beginning because all that energy gets dissipated. That's a misdirection. Don't tell them the energy at the end. Tell them the energy at the beginning. What's the total momentum after the collision? I don't know. I'm going to tell you the total momentum before the collision, though. It's the same number. That would be a misdirection. Derive an expression for the net torque exerted on the system as a function of time t. Okay, so what did we say? We said if omega equals omega naught e to the minus beta, I can't draw beta t. That is what it was, wasn't it? Yes. Then alpha is the derivative of this, beta naught omega naught e to the minus beta naught t. And then torque would be I alpha, which would be negative beta naught omega naught I system e to the minus beta naught t. What do I need mass and length for? All right, derive an expression for the angular displacement of the system as a function of time t. All righty then. Now we are talking my language here. Okay, now this is actually legitimately difficult. Delta theta is integral omega dt. It's kind of the same as delta displacement is integral v dt. We're going to integrate from negative zero, like a moron, from 0 to infinity. Oh, there's the graph for me, right? Why infinity? Because it reaches an asymptote. So really you have to integrate to infinity. All right, integral 0 to infinity of, there it is. Omega naught e to the minus beta naught t dt. Okay, if taking the derivative multiplies by negative omega naught, then taking the integral will divide by negative beta naught. Okay, please don't make me prove that. Go learn some use substitution. 0 to infinity. Right, plug in infinity, you get jack. Plug in 0, and you get minus a negative omega naught over beta naught. That's it. It's just omega naught over beta naught. That even has correct units. because I know that beta naughts units are 1/seconds in order for the exponential to have no units in it. So this would be radians per second divided by 1/seconds. That is actually radians. Okay, that makes sense. The three-blade system is now replaced with a second three-blade system, except that the slows down according to the same initial speed, and the beta is greater. If that's the case, if the beta is greater, then that means it takes less time to reach the asymptote, sarcasm quotes. Same shape of the graph, but it takes more time to reach the asymptote. All right. Well, I hope that was fun for you. I'm afraid to even look at the time code at the very last frame of this video because I think it's going to go on for even longer. I did all 9 questions of the BC Calculus yesterday, and it's on my YouTube. So if you're watching this on YouTube, you can see all 9 AB and BC, I meant to say AP Calculus questions. Remember, there are 3 that both exams have in common. It took me 75 minutes to go through all those. I'm afraid to even ask what this is. All right, well, I'm going to do electricity and magnetism next, so I hope you enjoy that one too.